Okay, welcome to section 2.2. We're going to do 2 days of notes here in this one screencast, but it's all section 2.2. So it's a very lengthy screencast, very lengthy notes. Feel free to pause the video if you need to take a break at any point. All right, today we're going to talk about polynomial functions, and we're going to talk a lot about finding zeros and graphing polynomial functions that are bigger than squared or even cubed functions. Okay. In 1.3, we learned about end behavior of a function, describing how the function behaves at either end of its graph. As x approaches positive, negative infinity, the end behavior of any polynomial function is determined by its leading term. We call this the leading term test. It uses the power and the coefficient to determine the end behavior. So there's basically 4 different types of end behavior we could have for polynomials. The first one, we have an odd positive, or a positive odd, whatever you want to call it. So you can think of that as a 2x cubed. That's kind of just like an example. So we can say, let's just do even 1x cubed, just to make it easier on us. So a positive number out in front, 1, and an odd degree, 3. Okay, so we know what that looks like. That looks something like this. Okay, and as x goes to negative infinity, y will also go to negative infinity. As x goes to positive infinity, y will go to positive infinity. Okay, so anything that has a positive odd, we call that, those would be the end behaviors. So, for example, 3x to the 5th or 8x to the 9th. Just a couple different examples. Then we have a positive even over here, so a positive even. So example we'll use for that would be just 1x squared. Okay, 1x squared would look something like this. Now I'm supposed to actually hit 0, 0 there. In this case, both left and right will be going to positive infinity. So any positive even will have both positive infinities as their end behaviors. Okay, next one we have a negative odd. So basically take that positive odd that we did and we're going to flip it. Okay, so this would be like negative x cubed. So that would look something like this. So now as x goes to negative infinity, y goes to positive infinity. As x goes to positive infinity, y goes to negative infinity. Okay, and then finally, a negative even. So for example, negative x squared would look something like this, both going to negative infinity. Every polynomial function will look like one of those 4 at the endpoints. So it's your job to figure out what kind of end behavior the polynomial function will have. So let's take a look at a couple examples. Describe the end behavior of each polynomial function. First thing you should probably do is make sure every equation is in descending order. All of these are, but just in general, make sure it's in descending order. Okay? So the first one here, we have a positive even. Okay, so positive even would look like this. So we say limit as x approaches negative infinity of f of x would be infinity. And limit as x approaches positive infinity of f of x is also infinity. The second one, b, we have a negative even. So end behavior will look like this. Okay? So that means both these answers will be negative infinity. So as x goes to negative infinity, y goes to negative infinity. As x goes to positive infinity, y goes to negative infinity. The third one, we have a positive odd. So a positive odd would look like this. So limit as x goes to negative infinity of h of x would be negative infinity. And limit as x goes to positive infinity of h of x would be positive infinity. And that just reminds me that letter B was not called f of x, so we need to make sure we name the functions properly. G of x. All right, the last one, we have a negative odd. So a negative odd would look like this. So limit as x goes to negative infinity of j of x would be positive infinity, and limit as x goes to positive infinity of j of x would be negative infinity. Okay, so the big part of this section is being able to analyze a function and its graph. So on the left side, we're going to talk about lots of rules. On the right side, we're going to do an example as we go. So the first thing we need to know is the degree. The degree of f is the highest exponent of x. So our example over here, what's the highest exponent of x? That would be a 3. And it's important to know it's the highest exponent of x if we multiply the entire function out. Now this one's already multiplied out, but sometimes it's not. We'll see that later. Next, we find zeros or x-intercepts or roots or solutions. Those all mean the same thing, but they're all written differently. Okay? So what we do is we set the function equal to 0 and solve. Okay? And for every number we get that works for that equation, x equals r is called a solution. Just r itself is called a real 0 or a root. And then remember, for an x-intercept, you have to write it as a point. r comma 0 is your intercept. And then the expression x minus r is called a factor of the function. Okay? Sometimes x minus r occurs more than once, and it's called a repeated 0 or a multiple 0. All right, so for this example, setting that equal to 0, we can factor out an x. And then factor that again. So there's two zeros. X equals 0 and x equals negative 2. And then negative 2 again, but you don't have to write it twice. So our x-intercepts would be 0, 0, and negative 2, 0. And the factors of p would just be x, and then x plus 2 twice. So we write x plus 2 squared. Which brings us to our next point, multiplicity. Multiplicity, if x minus r to the nth power is a factor of m, then r has multiplicity m. If it has even multiplicity, when we graph it, the graph will simply touch the axis and bounce back to where it came from. Okay? If it has odd multiplicity, so 1, 3, 5, 7, 9, the graph will go through the x-axis. It will cross the x-axis. So let's look at our two zeros here. We would say x equals 0 has, well, how many times does it occur? It only occurs one time here. So we would say it has odd multiplicity. So therefore, we would say either, you can say that it crosses the x-axis. However, x plus 2 occurs twice. So we would say x equals negative 2 has even multiplicity because 2 is an even number. So therefore, at negative 2, the graph will either, you can say, touch or bounce at the x-axis. Okay, we'll do a lot more of those problems today. A polynomial function has at most n distinct zeros. What is n? N is a degree. Okay, so in this problem, it could have at most 3. It doesn't have 3. It only has 2 distinct zeros, but it could have 3. And the number of turning points in the graph is at most 1 less than that. So in this case, it'd be 3 minus 1 or 2. So the graph could have 2 turning points. It might have 0, but it might have 2 at most. So that's it. Let's take a look at lots of problems from here on out. First one, it's already in descending order, so that's good. All right. The degree is 3. The leading coefficient is negative 2. So the end behavior would be limit as x approaches negative infinity of g of x, and limit as x approaches positive infinity of g of x. So let's figure out what the end behavior is. This is a negative odd. So negative odds would look like this. So this one would be positive infinity, this one would be negative infinity. The number of real zeros is the degree, so that'd be 3. For y-intercept, remember for y-intercept, we simply put 0 in for x. So g of 0 would be 0 minus 0 plus 0, or 0. So our y-intercept is 0, 0. For the x-intercept, here's where we're going to do some work. We're going to set g of x equal to 0. And I'm going to factor a negative 2x out. That leaves me with x squared plus 2x minus 8. So factoring again, and we get 3 x-intercepts. 0, 0, which we already knew, negative 4, 0, and 2, 0. Okay, all the exponents here are 1. If we don't write an exponent, obviously that means it's a 1 there. So they're all odd for our next part. When you do this, I recommend writing these in numerical order. So I would say x equals negative 4, x equals 0, and x equals 2. And then just one at a time, tell me what they have. So x equals negative 4 has odd multiplicity. You can use MULT for multiplicity. So what happens at negative 4? We're going to cross the axis. 0 has odd multiplicity. So what happens at 0? We're going to cross the axis. And 2 has odd multiplicity. So what happens at 2? We will again cross the x-axis. And finally, number of turning points. Remember, the number of turning points is the degree minus 1. So 3 minus 1, 2. Let's try another one. The degree here is 5. The leading coefficient is 3. So this is a positive odd. It would look like this. So limit as x approaches negative infinity of f of x is negative infinity. And limit as x approaches positive infinity of f of x is positive infinity. Number of real zeros at most would be 5. The y-intercept, f of 0, is 0 plus 0 plus 0, which is again 0, so y-intercept is again 0. All right, the x-intercept, so set f of x equal to 0. Let's factor out a 3x cubed, leaving us with x squared minus 6x plus 9. Factor it again. Or you could write it like this. So there's 2 x-intercepts, 0, 0, which we already have, and then 3, 0. 0 has multiplicity of 3, which is odd. 3 has multiplicity of 2, which is even. So when you write these down, x equals 0 has odd multiplicity. So that would be a cross at that axis. It's just going to go right through it. And then x equals 3 has even multiplicity. So what would happen there? You can say either would bounce or touch the axis. And finally, number of turning points is 5 minus 1, which is at most 4. Could be 4, could be 2, could be 0, but the most it could have is 4. All right, the next one, when it's in this form, this is called factored form, it makes the x-intercepts and the zeros much easier, but it makes the y-intercept a little bit harder. and the degree. All right, so the degree here, you might think it's 4, but it's not 4. Remember, degree is if you multiplied it all out, what would be the highest exponent in x? So if we multiplied all this out, the degree here is 0, the degree here is 1, 3, and 4. So what you're going to do to get to the final degree, if you multiply it all out, is add all those together. So 0 plus 1 plus 3 plus 4, our degree would be 8. The leading coefficient would be 1/2 times 1 cubed times 1 to the 4th. So it's just 1/2. So we call this a positive even, which would look like this. So our end behavior, oh, this one needs a name, huh? Let's give it a name, h. Of h of x would be positive infinity, and a limit as x approaches infinity of h of x would also be infinity. Number of real zeros matches the degree, so that's 8. Okay, like I said, the y-intercept is harder in this form. Okay, so h of 0 would be 1/2 times 0 minus 1 times 0 minus 3 cubed times 0 plus 2 to the 4th. So that's 1/2 times -1 times -27 times 16. Okay, so that basically, the easiest way to do this here is to do half of 16, which is 8, and then do 8 times 27. Okay, so 8 times 27, 27 times 8, 7 times 8 is 56, 2 times 8 is 16, so that'll give us 216. So our y-intercept is 0, 216. The x-intercepts in this form are much easier. It's already factored. No x-intercept from here, because that'll never be 0. But then we get 1, 0, 3, 0, and -2, 0. From here, here, and here. The multiplicity is also going to be easier. This is 1, so that's odd. This is 3, so that's odd. This is 4, so that's even. Again, write these in numeric order. I think it's going to make it a little bit easier for you when we get to the next part of graphing. So we say x equals -2 has even multiplicity, so that will touch the axis and bounce off. X equals 1 has odd multiplicity, so that will cross. And x equals 3 also has odd multiplicity, so that will also cross. And the number of turning points, remember, is degree minus 1, so at most 7. All right, at this point, why don't you pause the video and try example 5. When you finish, come back and you'll see me going through the answers. Okay, so there's your answers for example 5. Feel free to pause the video if you need to look at that for any longer. So the next day, we're going to do the same thing that we did, except now we're going to actually graph it at the end. Okay? So let's take a look at example 1. The degree here would be 2 plus 2 plus 9 plus 4. So the degree here is 19. The leading coefficient would be 4 times 1 squared times 1 to the 9 times 1 to the 4th. So just 4. So we call this one a positive odd. And here's your end behavior. Number of real zeros at most would be 19. The y-intercept here, well, this is nice. When you put 0 in here, you get 0. So 0 times anything would be 0. So our y-intercept is 0, 0. Always nice when that happens. Which means our x-intercept is 0, 0, but there's more. We also have negative 5, 0, 3, 0, and 6, 0. So let's go through their multiplicities. Again, I always encourage you to write these down in numeric order. So negative 5 has even multiplicity, as does 0 and as does 6. 3 has odd multiplicity. So at negative 5, we're going to have a touch of the axis, and we will also have that at 0 and at 6. However, at 3, we're going to have odd multiplicity, so at that point it will cross through the axis. Turning points at most would be 18, and now we sketch it. So how do we sketch this? Well, first of all, we have 4 points in this graph. Let's plot those 4 points. Negative 5, 0, 0, 0, 3, 0, and 6, 0. We also have the end behavior. We know to the leftmost point of this graph, it's going to be going down forever. And at the rightmost point of this graph, it's going to be going up forever. So that's everything we have up to this point. Okay? We also know that at negative 5, it's going to bounce off the axis. So at negative 5, you can imagine the graph is coming from down here, right? So it's going to curve back. It's going to touch the axis and curve back. Okay? Then at some point, it's got to curve back towards the axis. And at 0, it's going to touch it again. So at 0, it's going to bounce off again. And at some point, again, it's got to curve back towards the axis. But this time at 3, it's going to cross through the axis. So it's going to go through the axis at 3. We know it has to turn back to the axis again. And then at 6, once again, we're going to touch or bounce off the axis. So that is everything that we know. Let's count our turning points we have. 1, 2, 3, 4, 5. I don't think that's 18. Right? Actually, there's 6. 1, 2, 3, 4, 5, 6. Still not 18 though. So we don't know if this is the completed graph or not. There may be, there may be more turns over here, or there may be more turns over here, or over here. We don't know. So because of that, I can't just fill in this graph with a solid line because I don't know exactly what the rest of this graph looks like. So what I'm going to do is I'm going to dash in the rest of it saying, I'm not sure what this part looks like, but I know in general this is what the graph has a shape of. Feel free to rewatch that if you need to go through it again. All right, example 2. The degree here is 0 plus 2 plus 2 plus 5. So 9. The leading coefficient is negative 1/12 times 1 times 1 times 1, so negative 1/12. So this is an odd, a negative odd, so it would look like this. So here's our end behavior. Number of real zeros matches a degree. The y-intercept, so h of 0, will be negative 1/12 times negative 3 squared times negative 2 squared times 1 to the 5th. So that's negative 1/12 times 9 times 4 times 1. Okay, so that would be negative 1/12 times 36, or negative 3. So our y-intercept is 0, negative 3. X-intercepts would be 3, 0, 2, 0, negative 1, 0. So again, write them in numeric order here, negative 1, 2, and 3. Negative 1 has odd multiplicity because it's to the 5th power. So we'll cross there. 2 has even multiplicity because it's to the 2nd power. So we'll just touch the axis there. And 3 also has even multiplicity because it's squared. So we'll touch the axis there. Number of turning points would be 9 minus 1, at most 8. And let's sketch our graph. Again, remember to sketch a graph, start by plotting the points we know. Again, we have 4 points that we know. 0, negative 3, negative 1, 0, 2, 0, and 3, 0. Now our end behavior. We know our end behavior will look like this and this. Okay, starting from the left side, we know it's going to cross through negative 1. It's going to go through the y-intercept here, come back to the axis. It's going to bounce off of x equals 2, come back to the x-axis, and bounce off x equals 3. So we have 1, 2, 3, 4 turning points, which is not 8. So we cannot complete the graph. We'll dash in the rest. And this is the general form of what that graph would look like. All right, example 3, we're kind of moving backwards here. We give you a graph and we want you to write a function that fits that graph. Okay? So first thing we should do is determine the end behavior of f of x. Looks like both are positive, infinity. Okay, so what does that mean? That means this is going to be a positive even function. Okay, the least possible degree. So the least possible degree we're going to get from the turning points. It's going to be 1 more than the turning points. So I see 1, 2, 3 turning points. So the least possible degree would be 3 plus 1, which is 4. Just like how we used to get the turning points by subtracting the degree. This time we get the degree by adding the turning points. All right, the zeros and the multiplicity. We have 4 zeros. X equals negative 5. X equals negative 1/2. X equals 3, and x equals 5. What are their multiplicities? Well, we don't know the actual numbers, but we know if they're even or odd. If it goes through the graph, it's odd. So at negative 5, it's odd. At negative 1/2, it's odd. At 3, it's odd. And at 5, it's odd. So they're all odd. So the final thing says create a function that fits this graph. All right, so I know it's called f of x. F of x equals, leave a little space here, you'll see why later. Okay, and then I have x plus 5, 2x plus 1, that's where this comes from, x minus 3, and x minus 5. Okay, so why do I leave a space here? That's for the leading coefficient if it's not what we think it is right now. All right, because all of these are odd, you can put any degree on those that you want as long as it's odd. Big hint, if it's odd, leave it as 1. Otherwise, your next part is going to be way more complicated. If it's even, leave it as 2. Okay, but because all these are odd, we're going to leave all 4 of them as 1. All right, now if you were to put 0 into this, you would get 5 times 1 times negative 3 times negative 5. So that would be 75. Okay, look at your graph. Is f of 0 75? I don't think so. F of 0 is 1. So what do we multiply 75 by to get 1? 1/75. That's why we left a space there. Let's look at another one. So the end behavior here as x goes to negative infinity, we have negative infinity. And as x goes to positive infinity, we go to positive infinity. Okay? Turning points, 1, 2, 3, 4. So this would be 4 plus 1. The least possible degree would be 5. My graph here is a little off. I wanted this to be easier on you than it looks like it is. So let's just pretend that this is negative 4, 0. This is supposed to be at negative 1, 0. And this is supposed to be at negative 6, 0. Oh, sorry, positive 6, 0. We don't want to deal with all these fractions, trust me. And our y-intercept here is 0, negative 2. Okay, so our zeros are negative 4, negative 1, and 6. Okay, once again, it's going through the graph at all 3 of those. So they're all going to be odd. So when we create a function here, it's called g of x. We have x plus 4, x plus 1, x minus 6. So if I were to put 0 into that, I would get 4 times 1 times negative 6, which is negative 24. I'm supposed to get negative 2. So negative 24 times what will give me negative 2? And the answer is positive 1/12. So we're going to put a 1/12 out in front there. And this is, again, just one example answer. There's many answers that will work, but this is one example. All right, example 5. Our end behavior. Limit as x approaches negative infinity of h of x is negative infinity. Limit as x approaches positive infinity of h of x is also negative infinity. There are 1, 2, 3 turning points, so the least possible degree would be 4. There are 2 zeros, negative 3 and positive 2. And at both of them, they are simply touching the axis and bouncing off. These are both even. So when we create a function here, h of x equals x plus 3. Now it's even, so it has to be an even power. Again, choose 2. Don't make it 4, 6, 8, 10, because otherwise your next part's going to be really difficult. Okay, so pick 2. And then we have x minus 2. Again, pick 2 for our exponent there. So when we put 0 in, we get 3 squared times negative 2 squared, which is 9 times 4, or 36. But our actual y-intercept is negative 1. So 36 times what would give me negative 1, and that would be negative 1/36. Okay, for the last thing, we need our calculators out, graphing calculators out. So if you want to get one of those out right now, go ahead. And let's go ahead and type that function into y1. All right, you can play with the window first, or you can just graph it right away, and then you can play with the window after that. So let's just take a graph. That is not a good enough graph because we don't see all the turning points. So we need to make our y minimum much lower. And I'm also going to shrink the x's a little bit as well. So I'm going to go from negative 6 to 10. And my y min, I'll make negative 25 and see if that helps. Closer. All right, so I'm going to shrink my x's a little bit more and make my y minimum even lower. I'm going to go negative 5 to 6. And I'm going to go negative 35. That's a pretty good looking graph. Okay, so let me record my window here. You don't have to use the same window as me, but just in general, something that gets the graph visible. Okay, so if we were to sketch this, looks like we're crossing the axis around here, y-axis here, and then the x-axis here. So it should look something like this. So part B says find the intercepts. Okay, well to find the y-intercept, we don't need a calculator for that. If you put 0 in for x, we would get 0, comma, negative 3.8151. But it says 2 decimal places, so 3.82. All right, to get the x-intercepts, go to your calculator, second trace. Number 2 is 0. Go to the left of the 0, hit enter. Go to the right of the 0, hit enter. And you may have to hit enter one more time to get that. And of course my app isn't working. That's the beauty of these apps. Let me get my calculator out. You may have to give me a minute because I have to retype my function in. Maybe you can fast forward. Oh, okay. I know why my app is not working properly, because if we were to zoom in on that area right there, it actually crosses through the axis twice. So we got to find multiple areas. So let's do that. Let's zoom in on that. So I'm going to zoom in on this area right about there. So to do that, I'm going to change my window to, let's say, -2 to 1. And we're going to go -5 to 5 for our y's. I put 61. That's not what I want. 1. Okay, now I have a clear picture of what I need. So now in your calculator, you can do what I was saying to do before. Go to second calculate, and then number 2 is 0. Go to the left of that 0. And then hit enter. And then go just to the right of that 0. And hit enter. And then if you have a TA83 or 84 like I have, you'll have to hit enter one more time. The calculator needs you to take a guess. So just scroll as close to the 0 as you possibly can. And hit enter one more time. And I'm getting -0.899999, which is essentially -0.9. So -0.90, comma 0. Okay. Now if we want to take a look at the other one, the other 0, I know it's a positive one, so maybe we'll go -1 to 5 now. And you can see it over there. Actually, let's make the window even better than that. Let's go 0 to 6. So we can really see that 0 there. Okay. Go second calculate. Number 2 is 0. Scroll over a lot until you get just to the left of that 0. So you want it to be just under that x-axis. There, about there is good. Hit enter. And then just to the right of it, hit enter one more time. And you can see I'm getting about 4.71. So 4.71, comma 0. Sorry for the bad handwriting here. So we have all of our intercepts. Done with that. All right, next one says determine if the x-intercept is odd or even. Well, we have 2 zeros here. If you look at the graph, at -0.9 it bounces off. So that one is even. But at 4.71 it crosses through. So that one is odd. Okay. I'm going to go back to my original window here so we can see this whole thing again. So part D says find the power function that the graph resembles. So this one is essentially a multiple choice question. Okay, is it positive x squared, negative x squared, positive x cubed, or negative x cubed? Okay, and for that you want to look at the end behavior. Our end behavior looks like this. So this is a positive x cubed. So you're going to write y equals positive x cubed down. The number of turning points in the graph is simply 2. Local max and local min. So we did this in the last chapter. Let's remind you how to do that. Go to second calculate. Maximum or minimum. Let's do the maximum first. Let's do the minimum first because we're closer to that, I think, in the cursor. Find your minimum. Go just to the left of it. Go just to the right of it. And our minimum is -26.16. Or -26.157 to the 3 decimal places. So min is -26.157. Now to find the max, so calculate the maximum, number 4. Scroll all the way over to that. Or if you were smart enough to realize this, that maximum is just our intercept. It's 0. Okay, part G says find the value of the function when x equals -10. So for that one, all you're going to do is second calculate. Number 1 is value, and then you're going to type in -10. And our y value is -1218.135. So you can say f of -10 equals that. And finally, h is saying, all right, if y is 3.5, what's x? So to do that, you're going to go back into y equals. You're going to go to y2, and you're going to type in 3.5. And graph it, and you should see at least one intersection point. And we do. We see 1. So to find that point, you're going to second calculate intersection, which is number 5. And just scroll over as far as you can to try to get right on top of that intersection point. And enter. Let me try that again. Looks like it's at 4.817, comma 3.5000. Okay, so we already know it's 3.5. That they gave us that. So our x coordinate is 4.817. Okay, that's it for section 2.2. We'll be back for 2.3